So previously we had talked about what cryptography is, or at least gave ourselves a kind of a broad view of it. We also introduced some key ideas such as the communication channel and what a cryptosystem is. We talked about it in a broad sense because there's many kinds of cryptosystems. But we're going to start off just to illustrate these concepts with a fairly basic cipher from classic cryptography called the shift cipher. So by the end of this, you should be able to pick it up and have some little bit of fun with it. So I encourage you to play with it with your friends, okay? So here's the idea in the shift cipher. So imagine I have my plaintext. This is the message you're going to want to send over the communication channel. And I must stress that once we've encrypted the message, it gets sent over the communication channel over to the other agent for decryption. And the person that sends the message and the one that receives the message, they'll have the keys to do their tasks of encryption and decryption, respectively. So they have agreed upon what the keys will be. So here's the idea for the shift cipher before we get into the definition that we're going to have. So what we're going to do is we're going to take symbols in the plaintext, and shift the value, I'll kind of colloquially use the word value here, of each symbol in the message or plaintext by an amount. And you might ask, what's the amount? The amount is the key. Keep it simple like this. So I must stress that this is fast and easy to compute for encryption and decryption, right? If I shift, so imagine I take each one of the symbols, and I'll get into more detail what I mean by shifting the value of a symbol. But this idea of just taking, imagine each symbol has a value, I add or subtract that value, and then I get another value for which there is a symbol. Should be fairly easy for me to carry out using modular arithmetic. Well, just doing some basic arithmetic, I'm able to carry this out. So here's the definition of a shift cipher using our concept of a cryptosystem. So we're going to define it in terms of reading each symbol in the plaintext. So our notion of the plaintext applies to the whole message, but also within the context of our definition here, it may as well apply to one of the symbols that's a part of the message. For us, it doesn't make much of a difference. You're going to do this to the entire message anyways. So fix sum. So we're going to fix sum b, which is going to be a positive integer. So this is going to be a constant. So consider when the possible plaintext is equal to the possible ciphertext, which is going to be equal also to the keys. It's going to be equal to the set of all integers, where ZB here, fancy ZB, this would be equal to 0, 1, 2, all the way up to, but doesn't include B. It goes up to B minus 1. So for example, if I had Z26, that would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 25. So that means that the plaintext ciphertext can be interpreted, so our symbols that we're going to have, that's what I want you to think about this as. They're going to be represented as numeric, they're going to be numbers. That's how you can interpret them, but they're going to have corresponding values for their symbols. Consider when those are all equal. So I haven't addressed the encryption and decryption yet. For each key K, that's going to be between, but includes 0, but doesn't include B, let the encryption with the encryption and decryption of symbols XY in ZB in plain text. So we're going to be talking about the symbols in the plain text when I define this. Plain text and ciphertext, respectively. To be defined as follows. So I'm going to define it as follows. So naturally, I got to tell you what E is and what D is for a given key K. So just keep in mind our idea here. So I'm going to interpret the symbols X and Y as numbers. So EK of X is going to be X plus K modulo B. So I'm going to take whatever the numeric representation of that symbol is. I'm going to add K to it. That's the key. I'm going to reduce modulo B. And decryption will be done on a symbol Y, where I just simply subtract off the key value, modulo B. So this is how I'm going to define the shift cipher for you. Often in practice, what will happen is you'll have it where B is going to be a number that's going to correspond to the number of symbols that are going to be possible in your messages, hence why these are all equal like this. For example, if I'm just going to care about alphabetical symbols like A, B, C, D, E, F, G, but only one case of them, then it's 26, right? Because there's 26 letters in the English alphabet. So keep in mind that the setup here is that somebody's going to decide on what B is, and then they're going to have some key. And then I'm going to have for each K, for each one of the Ks, so those are the possible keys, I'm going to have EK and DK defined as follows. So remember this it's going to be applied to each symbol in the plain text for EK, and it'll apply to each symbol in the ciphertext DK. So in this scenario, this is just the exact one I talked about when I talked about with the crypto system, is that, and this is fairly common, is you'll have it where on each one of the symbols in the plain text, you're going to apply our encryption rule or encryption algorithm, or encryption, and respectively decryption. So just to come back to this idea, that you can have a value for each symbol. This is not a strange concept. This happens all the time in computing. For example, you might know of ASCII. So ASCII is a fairly common standard for which symbols have corresponding values on your keyboard. So very often what you'll do is you'll have it where you have like all your ABCs, you may have periods, you may even have special symbols for things like a space that I won't go into too much detail here. I put a link in the notes to discuss this more about ASCII. But the point I'm getting at is that in practice, if you're trying to implement one of these and you just want to care about alphabetical letters, what you would do is you would take each one of the symbols, you can cast it, that's a programming mechanism, you cast each one of your characters in the string, your symbols, each one to be an integer. And they correspond to different types of values, such as ASCII. There's other standards that also exist. But the thing is, if you want to keep it so it's between this range, in practice what you do is you would subtract off the offset for which that character set begins at. For example, the uppercase letter A doesn't actually sit at 0 or something like that, or lowercase a doesn't sit at 0. It sits higher up in the ASCII values. So if you just check out the link, you just simply subtract off that little bit amount, when you're undergoing this process. So that's just one other detail here. But for us in our discussion, we'll just simply use a table that gives us the corresponding values for each one of the symbols. So this is what a shift cipher is. We're going to do some examples. But suppose we wish to encrypt some English text. So we're going to consider b is equal to 26 and assign each number in Z26 a letter. So just to elaborate what I mean, 0. So if I give you 0, this is the same as me saying A. 1 is B. 2 is C. And so on. So we'll make a table to help us do this. So to carry out this process, as just to elaborate here, remember, you're going to take each symbol in the plaintext. You're going to apply EK of whatever that symbol is. You'll end up with a symbol for the ciphertext. You're going to apply this to each one of the symbols because your plaintext will look something like this. You feed each one of these XI values over here. And then as a result, you end up with a corresponding symbol for the ciphertext. And you'll end up with a resulting ciphertext at the end of this. Y1, Y2, and so on, Ym. For which the result of this becomes Y1, for example, if that was X1. So you just do this for each one of these. And when you want to decrypt, you take each one of those. So for example, Y1, the first symbol, I give it over here, and then I end up with getting X1 back. So as long as you understand the process here, it's a piece of cake, right? You just apply this to each one of the symbols. So I have some more details about this in the notes, but let's make a table to help us understand how to carry out this process. So what's the process of doing this? So let's do an example. Let's go step by step through this. So suppose we encrypt using a shift cipher with key k is equal to 7. So we're going to use 7 as the key. The following plaintext. So what we're going to encrypt is we're going to encrypt the message. I usually put the plaintext in lowercase letters to keep this simple. It's going to be "Have a beautiful day." Sounds like a pretty appropriate message. Have a beautiful day. So what's the first thing I need to do? To understand what each of these correspond to, I need to convert them over to being what their values are. So we're going to use this table to help us do that. So the first thing we're going to do is to take each symbol and give its value. So we're just going to cast with the, so you can think of this just as casting if we're to implement this. Or if I had a table that told me what each value is, I might use that as well. So take each one of the symbols and give its value to produce a number sequence. So this is one way of going about it. So if we look at our table over there, the first, we have H. H is 7. A is 0, right? A is 0. V is 21. Let's see, we got E. E is 4. A is 0, right? Then now, actually, let me underline these as we're going so we don't lose track of things. So we got B next, that's 1, right? E, 4. A is 0. U is 20. T, got 19. I, 8. I is 8. Then we have F is 5. U, we've got 20. Got 20. Then we got 11, right? 11's I. No, wait, 20. No, 11 is L. Yeah, L. I was about to say I for some reason. This is why we have to be very careful. Make sure you look carefully at the table and make sure you're transcribing the letters to numbers carefully. So then I got D. D is 3. I'm just going to put 3 over here because I'm running out of space on that side. So D is 3. And then we have A is 0, right? And Y is 24. So here's our number sequence that represents the values of each one of these. Now, next step, we're going to take each number X and we're going to apply EK of X. This will shift each one of the letters by the value. With wraparound, of course. With wraparound. Remember, we have mod, it's mod 26. So we're going to have wraparound. So I'll remind you about that in a moment. So remember, it's X plus the key mod B. B is 26 here. So we're going to shift each X by K mod 26. So we're going to take each one of these numbers, we're going to add 7 to it, and then we're going to apply mod 26. So for those that aren't acquainted with modular arithmetic, is just if ever we go up to 26 or higher, it wraps back around it. 26 mod 26 is 0. 27 mod 26 is 1. Think of it as the amount of remainder it is for which if I divided one number by 26. So let's go through each one of these numbers. We're going to add 7 to it. So 7 plus 7 mod 26 is 14. 0 plus 7 mod 26 is 7. 21 plus 7 is what? Is 28, right? So 26 mod 26 is 0. 27 mod 26 is 1. 28 mod 26 is 2. Now next we got 4. 4 plus 7 is 11. 0 again, just 7. 1, okay, 1 plus 7, that's 8. I sure hope that is correct. 4, we got 11 again. Then we've got 7, again, because that's 0. 20. 20 plus 7 is 27. Mod 26, that should just be what? What should it be? Just 1, right? Because 26 mod 26 is 0. So that means 27 mod 26 is 1. Then, after that, we've got, let's see, 19 plus 7. That gets you 26. 26 mod 26 is 0. We have no remainder in that case. We have 8 plus 7. That is just 15, right? Then we have 5 plus 7 is 12. Then we have 20. We have 20 plus 7. So we have 27 mod 26. That means, remember, 26 mod 26 is 0, right? So 27 mod 26 is 1. 11 plus 7 is 18. Then we have our last 3 here. Well, 3 plus 7 is 10. We don't get anything by modding it by 26. Then we have 10, 7, and 5. Notice that 24 plus 7, what is that? What is that? Well, let's think about it. Let's think about it. So what would be 24 plus 7? So we have 24 plus 7 mod 26. Well, we know 26 mod 26, that's 0, right? 27 mod 26 is 0. Is it 0? No, it's 1, right? 28 mod 26, that's 2. But what is this number here? Well, I'll let you think about it. So anyways, the last number here is going to be 5. So now I have to take each one of these numbers and now I convert it back to being a symbol, its corresponding symbol. So I've applied the encryption now to the numbers as per our rule over here. Now we need to actually represent them as symbols. So convert, resulting sequence back to symbols. So we're going to turn it back to the symbols to yield the ciphertext, right? So all I do is I go through each one of these and I read off what the symbol would be for each one of those. So let's take a look. We have 14. 14 is O. I'm going to write it in capital letters as per our discussion in the past. So 7 is H. Then I have, actually let me underline these as we're going. 2, what's 2? C. Then next, 11. 11, right? That's L. Then we have 7 again. Number 7 is H. Then I have next 8, I, right? Because that's the next letter over anyways. I, 11. What's 11? Well, it's L again, right? We have L again. Then we have 7 again. 7 is H. Then we have 1. 1 is B. Then I have 0. That's just A. Easy peasy. We got 15. That's P. Then we got 12. 12 is, where is 12? Oh, it's over there. Got M. Then we have 1. That's B. Let me just make that M a little better. Make sure it's clear that that's an M. B. And then 18. 18 is S. S. Then we got 10. Yeah, 10 is K. Then we have, lastly, 7. 7 we've already established is H. And lastly, we have 5. 5 is F. And there we go. Now we got our resulting ciphertext. So this is what you give your friend if you don't want your other friends to find out what the message is. At least presuming that they're not very good at or astute to notice this kind of trickery that we're doing. We'll talk more about that in the future. So let's talk now about how we would decrypt this. So let's walk through this process, and fortunate for us, this process is essentially just the same thing but in reverse, right? But the thing we have to be careful about is how the decryption works. So remember we applied to each one of the symbols, but we have to be careful, right? Because there's a technicality around modular arithmetic. Remember, dk of y is y minus k mod b, right? And b is 26 for us. So one thing we have to think about carefully, for those that are astute about modular arithmetic, you might know that, oh yeah, you can have negative numbers for a mod. That is true, and I want to talk about this now. So when you subtract off k, there's a very real possibility. Remember how we had a wraparound effect that happened? Where if we go over, we have 26 or higher, it wraps around? Well, we have the opposite effect happens when it's negative. It's walking backwards. Instead of going back around like this, back to 0, you go backwards up to 25, then you go 24, 23, 22, and so on. So that's how this works. So just to give you some examples of what I'm talking about. So if I give you, for example, minus 1 mod 26, this is equal to 25. So that's 25. How about minus 5? Well, walk backwards, right? Remember, 0 mod 26 is 26. Minus 1 mod 26 is 25. So walk backwards from 26. So we know 0 is 26. So 25, 24, 23, 22, 21, right? And of course, minus 27 mod 26, if you really want to go have some fun with this. Well, it's 1 higher than 26 originally. So being minus that, it just means I'm going to shift over really by 1 because it goes the whole way around. If you think about it like a clock. So I just want to make sure you're aware of this. So we're going to walk through this process that I have over here, back upwards. So we're going to try to get back, have a beautiful day. So I was thinking, why don't we do it over here? Because I really want to convince you that you get back what you originally had. Now, for those that are possibly astute about this, you'll see quite quickly that it is going to give you the same thing back. But I want to make sure we walk through it carefully, so that way you understand the decryption process. So remember, we're going to take each one of the symbols in the ciphertext. We're going to apply the decryption rule, or decryption, which remember, it is just simply whatever the number, its corresponding number is, minus the key. Remember, our key is 7. Then you apply mod 26, because B is 26 here. So let's decrypt the ciphertext. So what I have over here is what Alice would do. What we're going to do is we're going to do what Bob does. So what we're going to do is we need to take all of these ciphertext symbols, convert them over to being a number sequence again. So we're going to take each one of these, convert ciphertext, the ciphertext to a number sequence. As before. So we're going to go through each one of those. I'm going to now write out what those would be as numbers. I'll give you a heads up, it's going to be the exact same sequence I have there, but remember, I really want to convince you that this is going to be fine. So let's see here. So we got O. O is 14. So O is 14. Next we have H. H is 7. C is 2. Then we have L. L is 12. Or is it 11? It's 11. My eyes are deceiving me here. So I'm just trying to show you what Alice and Bob would do. So Alice did all this work. Bob's got to do this work now. So now we got OHCl. So Bob receives this. And now we're going to keep going. So next we got H. H is 7. Right? Then we have I. I is the next letter over. That's 8. Then we have another H. Right? Another H. Let's see. You got 7, 8. 7, 8. Then we have L. That's 11. 11. Then we got H. That's 7. Then I have a B. So I have 11. Sorry, I have 7. 7, and then I have a 1. Then I have A, which is 0. 0, then P is 15. So I have 0, 15. 0, 15. Then I have M. M is 12. B is 1. 12. Then 1. Then I have S and then K. S is 18. K is 10. So we got 18, 10. 18, 10. Then H and then F. H, F. 7. And then, of course, 5. And there we go. We got our number sequence. Now next, what we need to do is we need to take each one of these. I'm going to now have to subtract off 7, then reduce to modulo 26, right? So we're going to shift backward by K for each Y in the ciphertext. So let's take each one of them and let's apply our process here. So 14 minus 7 is 7. Because remember, we know K is 7. That's what Bob knows. Bob knows that. So I have 7. 7 minus 7, 0. 2 minus 7. 2 minus 7. 2 minus 7 mod 26. What would that be? Well, let's think about it. Well, if I subtract off the 2, that leaves me 5. So I'm subtracting off 5 from 0. So it's 0 minus 5. So it's minus 5 mod 26. And we've actually established that this already was 21 earlier. Next, we got 11 minus 7. That's 4 mod 26. 7 minus 7. That's 0 mod 26. Got 8. 8 minus 7 is 1 mod 26. 11 minus 7, that's 4 again, mod 26. 7 minus 7, that is 0 mod 26. 1 minus this amount, well, it's 1 more than it would have been in the case that it will be shifted over 1 more than it was in that case, right? Right? So that'll be 20. Because if that was 21, this is 20. Then next, 0 minus 7. What is that? That's 19, right? Because that's 1 less than this one. And this one was 20. I encourage you to walk backwards. So imagine just like you're going through a clock, you're walking, instead of going clockwise around the clock, go counterclockwise around the clock. But imagine it's a clock that has numbers 0 up to 25. 2019. So let's see, we got this one, 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 and that one. 15. 15 subtract 7. What should we get? What's that? 15 minus 7. What's 15 minus 7? Well, subtract off the 5, you get 10. Then you subtract off 2, you get 8, right? Get 8. Then next we have what? 12. 12. Well, this should be 5, right? Take off 2 off 7, then you have 5 left. 1. Well, we already established for 1 that, how much is that? How much was it? It was 20, right? It was 20 mod 26 as a result after I go backwards, right? So I must stress that if you're implementing this, a lot of programming languages get this mod operator incorrectly implemented. It doesn't handle the negative numbers. So please be mindful of this. You might want to write your own. If not, just write your own function, then add in the functionality for the negative numbers if your programming language doesn't support that. So next we've got, what do we have next? So we have 12, we took care of 1, right? 18. 18 minus 7, that's 11. That one's easy. How about 10? 10 minus 7, that's 3. 7 minus 7, that's 0. Mod 26, 5. So now you got to go walk back 2 steps. 24. Go 25, 24. So these are all of my shifted values. I shifted back by k, which is 7. And now we got to convert it back to symbols, right? Finally, convert each of these numbers back to symbols. So let's read them off. So let's look at our table. So we got 7. 7 is H. 0, 1. 21. 21 is V. Whoops, I'm getting really excited here. 4, E. 0 is A. 1 is B. 4 is E. 0 again, A. 20 is U. 19 is T. 8 is I. 5, F. 20, U. 11, L. Then we got D for 3, A for 0, and 24 is Y. And have a beautiful day. There you go. There you go. That is the shift cipher.